then there'd still be some kid that goes, I've never seen that before. I don't know how we're going to start planning, but they better not jam-pack us full of meetings this year, because we're going to need more practice to figure out how to redo the whole semester and kind of correct or we can't just jump in assuming like we did.
Hey guys, am I audible today? Let me just tell you that they seem to have changed the options that are available to me. So if you do come in on the waiting room, I'm going to have to admit you one at a time now. Until today, it was possible for me to turn off the waiting room once the meeting started, and that seems not to be the case anymore. So get in the habit of entering by way of, somehow there's a UT connection that enables you to sign in. All right. Ooh, where is everybody today? We have a low participation rate.
I think we're going to have to add, I think we're going to have to make it, we're going to have to wean in.
Is it your wife talking in the background?
Oh, she's on a Zoom meeting too. I don't know what to do about that. Yeah, in fact, I should keep my voice a little low so that she doesn't hear me in the background. She's a high school math teacher, and they're trying to figure out how to help their students as well. So everybody's trying to make do with the technology that we've got. All right. Well, anyway, let's get started. So when we last left our heroes, we were working on this change of variable theorem, and I had several people writing to me very confused because I think that, well, several points of confusion, but the one that seemed to be bothering people the most was trying to figure out which way the coordinate changes are going. So I have a request for you guys. I'd like you to work on a problem from Calc 2 to see how you can handle changes of variables in an integration problem in exactly a Calc 2 kind of setting. And I don't need you to compute the whole integral, but I do want to see what you would do to get started. So let me spin this around and I'll give you a problem to work on for, let's just say, a minute or two. You should grab a piece of paper and a pencil if you're not already in the habit of using one. Okay, oops. So here's an example question from Calc 2. Please evaluate, or at least try to tell me how you would evaluate this integral. It's a definite integral now, and it's got a kind of a messy integrand, but I know that you guys have discussed more than one way that you could try to solve this problem. So take a minute, get started, and then I'll interrupt you and ask you how you did it. I feel like I should have Jeopardy music playing in the background. Do 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 All right, as you're working this, you know that at the end of the day, this should come out to be a number. This is asking you for the area of a particular region under a very specific curve over a very specific interval in the XY plane. So there's some number involved. I actually don't know what the number is going to be. I don't know the full answer. But I want to know what you guys did to start evaluating this. Would somebody like to share what they did to attack this problem?
I used trig sub.
Trig substitution. Okay, so specifically, what did you substitute? How did you begin?
Well, first I factored out the 4, so it's in the form of 1 plus something squared. So in this case, it'd be x squared over 4.
Yes.
Yes. Yeah, x over 2 squared. Yeah. And then I said let x over 2 equal tangent theta.
Mm-hmm. There's you. Okay, so that's your thinking. So you're going to say let x, well, x over 2 is equal to the tangent of theta. And if I can move the 2 to the other side, you would write it this way. Right?
Right. Yep.
And then, of course, now you guys know the steps that you were supposed to go through when you discussed the trig substitutions in Calc 2. There was a different way that you could have started the problem, though, besides this. Did anybody have a different kind of substitution or something that you might try? No? No other takers? All right. I actually worked it out in advance both ways, or at least I started it both ways so that I can show you what it is that you could be doing. So the method that he just proposed is right here. I don't know if you can see that. I wrote it smaller. So he proposed the substitution where x is equal to the 2 times the tangent of theta. Then the next step would be to calculate the differential. You would have to be differentiating this expression. Don't forget the d theta at the end. And now you have something that you can substitute in the original problem, both for the integrand and for the differential. So the integrand itself, the square root of 4 plus x squared, has turned into this, 2 secant of theta. And the differential gave us another factor of a 2 with a secant squared of theta. You also have to change your limits of integration. Some of you maybe were not encouraged to do that. In other words, in your Calc 2 class, your teacher might have said, look, just hang on, look at this function of theta, find an antiderivative, and then after you get your antiderivative, which would be some other function of theta, then you can plug back in what the theta is in terms of the x's, so that you would have an antiderivative expressed in terms of x, and then you would plug in those 2 values of x. I don't do that. I encourage my Calc 2 students, so they can skip that step. I ask them to just rewrite the integrand and the differential, and while they're at it, they should change the limits of integration as well, figure out the values of theta that correspond to these 2 values of x under this correspondence. So now the whole integral, everything in the integral has been changed to involve thetas alone, and so you could plot this function. It's 4 times secant cubed of theta. Plot that as a function of theta over this region in the theta plane, and just integrate it. Find the area that's underneath that curve. As I said, I'm not interested in the numbers, and so I didn't go any further. But I do want you to see that I've got a new range of values on the theta that corresponds in a natural way to the range of values of x that I was given in the first place. There's that interval in the x-axis. Here's the corresponding interval in the theta axis. And I say that it's corresponding in the sense that I have these 2 formulas that go either way that allow me to compute x in terms of theta or theta in terms of x. I've written them down there. Those are functions that one of them is defined on the x-axis and it gives me thetas. The other is defined on the theta axis and it gives me x's. They obviously are inverse functions of each other. And whichever one of these 2 you prefer to think about, it shows you that that interval corresponds to this interval. Now, I said there was a second way that you could have gotten this, that you could have approached this integration problem by using substitution. That's not the only substitution that would naturally occur to a calculus student. I can tell you from experience that if I'd have given this problem to a calculus class, somebody would have tried this substitution. Obviously, you've got the square root of something complicated, so call that complicated thing a u, and then you're off and running. Once you've decided what the u is going to be in the u substitution game, then you differentiate this to get du in terms of dx. Of course, the goal is to get rid of the dx's, and so you divide through in this equation to solve for dx in terms of du instead of the other way around. Unfortunately, when you do that, you get some extra x's floating around, but that's not really a problem because from this top line, you could deduce the inverse function. Instead of getting u as a function of x, you can get x as a function of u. So that way, you can rewrite this expression for dx in a way that doesn't have any x's in it. And so now you can rewrite the original integrand in terms of u alone, and you can write the original differential in terms of u alone. And while you're at it, the same as I did for the trig substitution idea, I would suggest that you rewrite your limits of integration so that they involve u alone. And that's quite easy to do in this case. You just plug in those two values of x and you get that u should range from 4 to 8. I guess I should say u equals 8 up there. So again, I didn't finish computing this integral. This integral actually looks kind of annoying. It looks quite difficult. And so I'm not quite sure what I would do as a next step to figure out what this number is. But what I do want to convince you of is that I've rewritten this original integral, which asked me to integrate a function of x defined on this portion of the x-axis. Now I've given you a different function of u, which you have to integrate over this portion of the u-axis. This is the interval of u's that corresponds to my original range of x's. And when I say it corresponds, you can use the formula that says how to compute the u's from the x's, or the one that says how to compute the x's from the u's. They both work equally well to convince you that that interval corresponds to this interval. The reason that I want both of these things on the display at once is I want you to see that they're both a substitution method, but your perspective on them is different in the two cases, not because there's trigonometry here and not there. That's true, but irrelevant for us right now. The difference here is that in the one case, you took the existing variable x and you expressed it in terms of a new variable that was called theta in this case. And in the other case, you did it the other way around. You started off by introducing the new variable by telling me how it is defined in terms of the original variable. As I said here in this parenthetical remark, in both cases, you can do it the other way. I mean, you can say what x is in terms of the new variable or say what the new variable is in terms of x. It's just that for some of our substitutions, it feels more natural to write it this way, and in other substitutions, it feels more natural to introduce the new variable instead. Whichever way you do it, you can invert the formula to get the other way. And then, once you've got this pair of formulas, whichever route you're going to go through, once you've got that pair of formulas, you can start to get the differential that has to be removed from this original integral. You can either get it, in this case, you directly differentiate, you differentiate this formula to get the dx. And in this case, it's a kind of a two-step process because you first get du in terms of dx, and then you have to solve to get dx in terms of du, and that requires a little substitution to get all the rest of the x's out. And in both cases, then, you have to do some thinking to figure out the range of the new variable that corresponds to the original range of x's. I think for a lot of students, this is the one that's a little bit faster because you simply plug in those two endpoints into the formula that says what u is in terms of x. Whereas in this case, you have to say to yourself, well, geez, if x is going to go from 0 to 2, that means that the tangent part has to range from 0 to 1, and a range of thetas whose tangents go from 0 to 1 would be this range of angles. So this maybe requires a little bit more reflection in terms of how this function is behaving. I summarize this for my Calc 2 students usually by having them think about a little diamond. When I'm teaching Math 408D, I tell them how they can carry out substitutions between integrals expressed in one variable and integrals expressed in terms of the other variable. I don't care which one you consider the original variable and which is the new variable. But just so I have something to point to, I guess I'll say, suppose you have an integral that was defined in terms of one variable that I'm calling x1. So in the problem that I gave you guys, that would just be the x. And x2 will be the new variable, which is in one case called u, and in the other case I called it theta. You have your choice of starting in either one of these corners of a little diamond, you can either tell me how x is related to the new variable or how the new variable is defined in terms of x. Somehow there will be a function of the other variable involved. So this was a 2 times the tangent function, and this was the 4 plus a square function. By doing some algebra, you can transform it from one of these corners to the other. And that's what I did with you guys up here, was I inverted the formula that I had written down in the first place to get the new formula. Then, from these two corners, you do some differentiation to get a formula for the differential of the variable that's on the left-hand side of the equal sign. And in both of those cases, you're simply differentiating the formula that was on the right-hand side of the equal sign. If your goal was to get rid of x1 everywhere in the integration problem, then people who got to this corner, they either started in this corner or they started down there and then went up and then came over. Those people now have something to write in instead of the dx1. It's all this junk that only involves the new variable x2. Other people that started here, or they started here and then did some algebra to get here and then differentiated, those people now have an expression for the new differential in terms of the old differential. So they're in this position now. They have to first divide by that junk that showed up and then do a substitution to get rid of the old variable. So that's what I did here. I took this equation, I divided by the junk that was in front of dx1, and then what this formula says is I'm now substituting away the x1s to turn them into x2s. No matter which way you begin, you end up with both these two expressions that relate the variables back and forth, and you have a mechanism to substitute away the differential. And as you can see, it involves a derivative either way. It's either a derivative in the numerator, if you went this idea, or you ended up with a derivative in the denominator if you went the other way. And that's exactly what we see in here. If you start with this approach, you end up with that derivative up here in the numerator. This other approach, that easy derivative had to then be put into a denominator, which gave rise to this junk down here.
Professor?
Yes, go ahead.
Would you mind holding that paper a little bit closer to the camera, just like super fast?
So it's a little easier to see.
Yeah,
Oops.
my eyes are bad.
No, yeah, mine too. All right.
Very cool.
All right.
Alrighty, cool, got it, thank you.
I do want to emphasize that it's not so much the formulas that I want you to see in here. I just want you to see the pattern that in both cases, the problem was given in terms of the variable x and an interval of x's that was relevant to us. We made the decision that we would calculate this in terms of a new variable, call it u, call it theta, I don't care. And in each one of those cases, there would be a new interval that was involved. The new interval is related to the old interval, and there are functions that go both ways. The function that goes from this range to the x's, that's a function that I'm going to be calling capital T in the sequel, but there's also a function that goes the other way, which is the function that I've been calling capital W. And you have to just recognize that in some instances, the function that goes towards the x-axis is the more natural one to write down. And in other instances, it's the function that goes away from the axis that feels like the more natural one to write down. The naturality of it isn't really a mathematical concept. Mathematically speaking, there's functions that go both ways. So, I'll write down theorems that will apply to both of these functions. As you go to use it, this theorem that I'm going to give you, you have to recognize that sometimes it'll feel natural and sometimes it'll feel backwards. Okay, so that's a human thing, not a mathematical thing. All right, so this is the general technique for substitutions, and as I'm trying to emphasize here, you can start with either type of formula, giving one of the variables that has either introducing the new variable in terms of the x or rewriting x in terms of the new variable. All right, so I wrote it out in advance for you. Here is the theorem. This is the change of variable theorem. And the two examples that I just worked with on the previous problem Those are the special case where we have something in R1. We have two different intervals inside R1. And we have a function that carries one of those intervals onto the other one. Further, we have a function that we wish to integrate, and it's defined on this side. If that's the case, if somebody says, hey, I'd like you to integrate a function over a certain interval, that's exactly where we are here. This is the thing that I'm calling d sub 2, and the function that I'm asking you to integrate is this function. If someone says, please integrate a function over an interval, you can, by doing either of those two substitution techniques, rewrite it as an integral over a different interval. And then you're going to have to do two things. In addition to rewriting the different, to calculating what the new interval is, you had to rewrite the original integrand, the original function that you were integrating. That has to be rewritten in terms of the new variables. And you have to multiply by something that involves a derivative, not the derivative of the function you're integrating, but it's the derivative of this transformation function. And I want to stress that when you write out this theorem mathematically, the function that's involved that pairs off the two intervals is the one that goes in this direction. It goes from the portion, the version of the real number line that had the new variables in it, and it maps onto the version of the real number line that had the original variables in it. So you see two references to capital T in here. That capital T goes from this interval that is a range of u's or thetas, and I have to use the function capital T that maps from that one onto the interval of x's. So when you choose to do a problem like this using this trigonometric substitution technique, that is asking you to begin by writing down exactly such a function capital T. That's the function that expresses the x's in terms of the thetas. If you choose to do a u substitution technique, that's fine, but the first instinct of the thing that you write down, that's a function that's going the wrong way for the use in this theorem. In order to use this theorem, you would have to go and find its inverse function. You'd have to solve for x in terms of u so that you map to get x's from u's, just like I'm getting x's from the thetas. So these two versions of attacking this integration problem by a substitution method, they both work. They both actually will give you valid integrals that express the original problem in the new language. And in both cases, you will have changed the interval over which you're integrating. You will have changed your integrand, and you will have an additional factor that has to do with a derivative. And that happens to be what they are, the one-dimensional versions of what all the rest of this formula says. This part over here is actually pretty easy to compute. This is the part where I say you have to rewrite the integrand. That's me looking at the square root of 4 plus x squared and writing it in terms of either theta or u. In this case, people don't even hesitate to write down the new integrand because you knew that you chose u specifically so that this would simply become the square root of u. In this case, you had to work just a little harder, but all you really did was you looked at the integrand and you substituted what the x was in terms of theta. Of course, you had to use some trigonometric identities to simplify it, but this literally is just the square root of 4 plus the square of 2 times the tangent of theta. It just gets simplified by using some trigonometry. So I guess what I'm trying to convince you of is that however you thought of substitutions before, you were in fact using this theorem. It's just that you had much more pedestrian language in the setting of Calc 1. But you do have to recognize that there's the transformation function. In the one case, went from the new variable range into the original variable range. And in the other case, the substitution you wrote down actually went backwards and you had to do something in this direction. Now, with all that said, I want to show you that we've been using exactly this change of variable theorem when we did our polar coordinate calculations. So, oops, I want to save that one. So let me do some of those. I gotta go back up a little bit here. So we're done with that integral. Let's now look at the kind of integral that we had last time. I'm sorry, I don't even remember the function that was involved, so but I don't need to know it. But I asked you to integrate some function of two variables over a quarter disk. I don't remember what the radius was on my quarter disk. Let's have a radius of 3 today.
The radius of your disk was the unit circle.
Yeah, I don't want to use that one anymore. I want to use something with a radius that's not 1, because the problem with the number 1 is that when I should be writing an r times the cosine of theta, if r is equal to 1, then you don't even notice that there's a 1 missing. So today I want to do a circle of a disk of radius 3, a quarter of a disk of radius 3. So you notice that in this problem I didn't even bother to write in the differential. I should have written a dA if I'd have been talking about an area integral, because when we chop this up into pieces, we'll be measuring the size of the pieces as an area. In the example that you guys did in R1, you had these two intervals in R1, then the appropriate thing to say is, I guess I could write dL, where L stands for length, because that's how you measure the size of the pieces of an interval in the real number line. So I don't bother writing the differential in when it's clear how we're measuring size. I'll put it in here just for completeness. So what did we say to do? I tried to encourage you to see that there were 3 things that you have to change if you want to write things in terms of polar coordinates r and theta instead of Cartesian coordinates x and y. I mean, you're perfectly welcome to write this all in terms of the Cartesian coordinates. Thanks to Fubini's theorem, you can write the area differential as a product dx dy, and then you need to figure out your ranges of y coordinates. I guess in this setting, y would go from 0 to 3, and your range of x's, that would go from 0 to, I guess it would be 9 minus y squared. But if you don't use Cartesian coordinates, if you want to use polar coordinates, that's still fine, but you have to change all 3 things. Change the differential, change the integrand, and change the region of integration. So how would that be? Changing the integrand is probably the easiest of all, because all you have to do is to get rid of the x's and the y's. And the way to do that is to substitute in what x and y are. You know that when you switch from polar coordinates to Cartesian coordinates, the new Cartesian coordinates are calculated from the polar coordinates this way. So that's changing the integrand by just doing a substitution. That's what I said to do over here. You are composing the original function f with this function capital T that takes a portion of the r theta plane and transforms it into a portion of the xy plane. So the transformation that I'm using here, I should say this off on the side, the function capital T that goes from the r theta plane into the xy plane is going to be T takes those 2 numbers r and theta, and it spits out these 2 numbers, r cosine of theta, r sine of theta. So this much is just a substitution, or if you want to use a mathematician's language, you're taking a composite. The original function defined on the quarter disk spat out a real number for each such point, and this transformation capital T is now taking points in the r theta plane and spitting out points that are in the quarter disk. So this is just what you are writing down here is just the composite of f with capital T. So it's just a substitution. That shouldn't be scary. The next thing to change is the differential. And I tried to draw pictures of a circle, a quarter circle that was split up into little sectors. We've talked about this before. The way you would measure the areas of those little sectors is to multiply the outward length times the length of the arc in the inside, which would be the number of the radians that have passed by times the current radius. So you just get in the habit of substituting the area differential that's written as dx dy with an RDRD theta. Now, I did work this out with you last time, if I recall, to show that, yeah, if you actually take these formulas for capital T, differentiate capital T to get a 2 by 2 matrix with R's and thetas in it, and then take the determinant of that 2 by 2 matrix, you will in fact just get an R. So this extra fudge factor that shows up is the thing that should be there according to the change of variable theorem. It's just the determinant, well, absolute value of the determinant of the derivative of exactly this transformation. Then the third thing you need to do is to change your region of integration, because yeah, sure, we're integrating over a quarter of a disk in the XY plane, but what's the combinations? What set of combinations of R's and thetas do I need to get this quarter of a disk? And for that, I've encouraged you to scan this quarter of a disk and play exactly the same game we used in Cartesian coordinates to figure out the 4 entries in those limits of integration. You wander over this whole set and ask all of the points about their theta coordinates, and you record the minimal and maximal answers that you ever get. You get a 0 on the bottom edge and a pi/2 on the left-hand edge. And then, once you hold theta fixed, you have to scan this set, just this portion of the disk, just that line segment, talk to all of those points, and ask them about their R coordinate, and listen to the answers that you get. And in this picture, you can see you'll get R coordinates that go from 0 to 3. It's sufficient to do the little talking to the points that I've just described if you want to get these 4 limits of integration. But I would be remiss if I didn't point out that what you've just decided is that the region D1 that I'm talking about in this picture is a portion of the plane, specifically the plane that has got R and theta as its coordinates. You have to find out what region in the plane is transformed into the quarter disk, and that region is described right up here. It's the region of all combinations of R's and thetas that have, well, the theta coordinate can go anywhere from 0 to pi/2, and for every one of those thetas, the R coordinate can vary from R equals 0 to R equals 3. So if I do that horizontal line by horizontal line, I discover that my region of integration is just a rectangle. So this is what the set D1 looks like. D1 is the portion of the Euclidean space that's marked off by the new variables that you're introducing. It's the portion of that space that's carried by this function t into the portion of Euclidean space that we started with. To use this language down here, this rectangle is the set D1 in my 2-dimensional setting. It's playing the same role that these intervals D1 did in the 1-dimensional setting. They were both carried onto the interval D2 by the function capital T that expresses the original coordinates in terms of the newly introduced coordinates. Okay, so it's exactly parallel to this kind of a figure, but you have to follow the arrows that go into the original Euclidean space. In our case, you have to follow the arrows that go into this picture. Okay, so you can go backwards, just as in the 1-dimensional setting. I can find a function capital W that goes the other way. That's the one that says R would be square root of x squared plus y squared, and theta would be the arctangent of y over x. I can write that function down, but I don't actually need that one. The one that I need is the one that goes into the original coordinate picture. Okay, does somebody want to ask me a question about this much of the change of variable theorem? All right. I know it takes a while to get used to these. So let me do a couple more examples. I want to do one more example that's in polar coordinates, but I want to break you free of the thought that somehow when you switch to polar coordinates, everything is just always going to be number, 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 number. So here's another example. It's another integral, and this one is again going to be just in the plane. Suppose that I ask you to integrate some function. I don't care what it is. Let's just have 3xy squared. And I want you to compute an integral over the following subset of the xy plane. How about if I ask you for all of the points that are inside of a triangle? Now, there's no reason that you have to use the change of variable theorem to calculate this problem. Oh, let me give you a specific line here that's going to be the cap of the triangle. Let's just take the set of points where x and y add up to 2. There, and this is the horizontal axis, so that's the set of points where y is equal to 0. This is the vertical axis, so that's the set of points where x is equal to 0. And if you wanted to compute this integral using Fubini's theorem, you simply write down a double integration sign. You keep the function, unchanged. The area element in Cartesian coordinates is written as dx dy. And your limits of integration, let's see, I have y on the outside, so my y coordinates go from the low y coordinates here, which are obviously 0, up to the y coordinate at the top. Anybody want to hazard a guess what the y coordinate is up there? Come on, you know it.
2.
2. How'd you get 2?
Well, because that's where it intersects the line x equals 0. So
Yes.
0 plus y equals 2. So y equals 2.
Exactly. So what makes this point be, you wanted the point that had the greatest y coordinate. You know that that would be the topmost, northernmost point. You can see it. It's the intersection of this line and this line, which means that the coordinates of this point satisfy this equation and that equation. 2 equations, 2 unknowns. Solve those 2 equations. Obviously, x would be 0 and then y would be 2. All right, and then you hold the y coordinate constant when you figure out the range of x's. Here's where the y coordinate has been fixed. This is y equals a constant now. And if I want my minimum and maximum values of the x coordinates, I go as far to the left and the right as I can. The leftmost point is right here. It's the intersection of this line with this line. So it satisfies these 2 equations, which means its x coordinate is 0. The rightmost point is right there. It's the intersection of that line and this line. So that point's coordinates satisfy these 2 equations. And so therefore I can take these 2 equations and solve to get the x coordinate. It'll be 2 minus y. This is an easy integral. I'll let you finish. What I want to illustrate is that I can, in fact, compute this integral in polar coordinates. So how do you do that? Well, every time we do a coordinate change, we have to change the 3 things: the integrand, the differential, and the region of integration. Changing the integrand is easy. That's just a substitution. We're using this formula giving me the x coordinates. This formula gives me the y coordinates. And so my integrand is just 3 times r cosine of theta times r sine of theta squared. And of course, that's 3r cubed, something, something, something. That's step 1. Step 2 is getting rid of the differential. And for polar coordinates, you know that's easy. That's just r d theta. Step 3 requires getting the new region of integration. What is the region in the r theta plane that we're integrating over that corresponds to this triangle? Well, I think the easiest way to do this is to just start talking to these points about their r and theta coordinates. So to help you out here, I will draw the sets of points where the r and theta coordinates stay fixed. Here's the rays of constant values of theta, and here are the arcs, the circular arcs that have constant values of r. So the way I have this integral written out right now, I've chosen to put thetas on the outside, r's on the inside. So I'll first get my limits of integration on the theta. As always, you have to scan this set, talking to the points, asking them for the least and the greatest values of the theta coordinate. The theta coordinate goes up when you go counterclockwise. So I want to talk to the clockwise most points, that's any of these, to get their theta coordinate. And the counterclockwise most points, which are any of these, and I'll get their theta coordinate. And I guess you guys know that the theta coordinates are 0 and pi over 2 on those two extremes. Now you have to hold the theta coordinate fixed and talk only to the points that are in this line segment. I'm sorry, I went too far there. And you have to ask them for their r coordinates and write down the smallest and the greatest values of the r coordinates. The r coordinate is minimized when you go inward as much as possible, and in this figure you can see that you go inward all the way down to the origin. You get your maximum r coordinate by going outward, so obviously this is the point that's going to have the maximum r coordinate. All right, what is its r coordinate? Well, I got to know what makes this point be what it is, and what makes it be what it is that's the intersection of these two lines. All right, let's write down the equations for these two lines. Here's the equation for one of them. And the equation for the other one, well, it was previously written in Cartesian coordinates, but I can rewrite it in polar coordinates too by using this substitution. What makes that line be what it is it's the set of points where x plus y adds up to 2. So here are now two equations involving the two unknown coordinates of this point. Two equations, two unknowns, you solve them to get the r and the theta. Obviously theta is equal to whatever the current value of theta is, and then the r coordinate, on the other hand, you can factor out in r and divide by something, so that would give you this formula for your r coordinate. In terms of the current theta coordinate, I guess I could write c in there if I like, but my observation is that once I've held the theta coordinate fixed at some value, this formula tells me the r coordinate of the maximum r coordinate that I'm going to get, which is to say the r coordinate of that point that's furthest out. So that would be my upper limit of integration. Now again, as in the previous example, I have done it. I have changed the entire problem so that it's expressed in terms of polar coordinates. I rewrote the integrand, I rewrote the differential, and I rewrote the region of integration. What I didn't do is to actually show you the region of the r theta plane, but I can do that. It's easier in this case, maybe I'll put the theta on the horizontal axis and the r on the vertical axis, because you can see that my theta coordinates just go from a 0 to a pi over 2. And my r coordinates also have r equals 0 as one of their edges. The only thing that's a little mysterious is exactly what this formula of theta is, but that's a function of theta, and if you plot it with theta on the horizontal axis and r on the vertical axis, you will, as it turns out, get a curve that looks something like this. That formula over there, it actually has a couple of vertical asymptotes, but they're just on the outside of this region. One's at negative pi over 4, and the other's at 3 pi over 4. So that function stays bounded inside this interval of thetas. And this is now the region D1 that was described in the change of variable theorem. So this transformation, capital T, this one that we always use for polar coordinates, it takes all of these points one at a time. Every one of these points is a combination of a theta on the horizontal axis and an r on the vertical axis. Shove those combinations of numbers into this formula, and you will get a combination of x's and y's that lies on that triangle. Now, in this particular case, the problem was way easier to do in Cartesian coordinates than it'll turn out to be in polar coordinates. I mean, I can calculate this antiderivative with respect to r. That's not hard, but when I stick in this region, this upper bound on the r's, I'm going to get some horrible function of theta to integrate. You might try, if you want to stay with polar coordinates, you might try doing this, but use Fubini's theorem to write these in the opposite order. Put r on the outside and theta on the inside. That's actually horrible. That would actually be a terrible thing to do, because if you imagine, I would first be asking you to describe the minimum and maximum values of the r coordinate, and it's clear that you have a minimum value being r equals 0, and the maximum would be this point and this point that have an r equal to 2. But then you would have to hold r constant and think about the range of thetas, and Well, you see, for a small r, the range of thetas is you go from theta equals 0 to theta equals pi over 2. But for some of the larger values of r, your range of thetas isn't even a single interval. You can have thetas that range from 0 up to something, and then you have to add in an interval that goes from theta equals whatever that value of theta is to theta equals pi over 2. So you could, in fact, compute the integral in polar coordinates with the variables in the opposite order, but you would end up writing this as a union of 3 separate integrals over these 3 separate regions, where here's where you get a circle that's actually tangent to that line. So you'd have to compute this integral, which would have easy limits of integration. And then this one and that one, those would be harder integrals because I'd have really messy limits of integration expressing theta as a function of r right here and right there. So you could do it. Turns out there's not a lot of reason to do it in this case. Anything you want to ask me about that example? All right, I'm going to do one more example that actually comes up from a homework problem that a couple of people asked me about. And I have just enough time to finish this one, I think. Where did it go? I wrote it out in advance. There we go.
Professor?
Yeah, go ahead.
Is it okay with a little bit of time at the end that I ask you some questions about how exam 2 will work or how you want to finish the rest of the semester? Is that okay?
Yes, well, that's a good question. So our exam 2 is, I believe, scheduled for 2 weeks from today. Is that correct?
I think so.
Yeah.
But what format will it be in?
Well, I don't really know. What would you guys like me to do for you for this exam? My default going at the start of the semester was we were going to have a bunch of multiple choice and then some free response, because that way I can grade it pretty fast and see your work. Well, if you did free response, how are you going to submit your answers?
Right,
And,
you have to like take a picture or something.
Yeah.
It just, to me, seems like I took like 6 pages just to finish one question, and if I do one thing wrong, it would be wrong, and you wouldn't see that I understand a lot of other things. So I don't know how other people feel.
well, so that's a good question. So your observation, does that tell us that we need to have more multiple choice or more free response? Or
So on Canvas, there's like a way that we can upload, like we can download your test and then re-upload our responses. So you could have it the same format as you had originally, and you just have it for that specific amount of time for a certain window.
Yeah,
like.
I would get PDFs from each of you. Now that would require that you have some way of scanning. There's little apps you can put on your phone that are not hard. Some of you may have scanners that would do it more easily. There are a couple of tools that I know they're put in as apps within Canvas, something called Grade Scope and something called Speed Grader. I have not used either of those. I'm actually kind of reluctant to try to learn how to use them just for the one remaining midterm exam and the final. I mean, the easier thing to do would be to give you an exam that's all multiple choice, a bunch of questions. Quest is set up to have an exam that you would have a certain amount of time to work on it. I would give you guys plenty of time because I know some of you are not even in the same time zone as Austin anymore. So I could do that. I can tell you pedagogically, that's a really lousy way to assess student understanding, in part because of what you just said, that you could have a long calculation that gets screwed up at the very end. But on the other hand, it's easier for you guys because you basically just sit at a screen and you click a few buttons and then you're done. So, I don't know, somebody chime in. What else do you want me to do? So a couple of you have spoken up.
If I can kind of interject, my thinking is like, I would kind of prefer having opportunity to just upload my work. For example, like your same format that you had, and then just upload work. I personally took an exam like that, and it wasn't very stressful in the sense of like, oh, like, am I going to get at least partial credit unless you can see our work? So that's kind of my thinking, is that by doing the method that I think it was Brianna that mentioned it, how you open the test for a certain number of hours, we then have to scan in our work. That way you can kind of see it and we can at least get partial credit. I'll feel more comfortable with that than just doing quest questions where one miscalculation just gets you a question completely wrong.
I totally agree with that, just because these are really, really, really long questions, and there's a lot of ways to show that we understand the concept, and having partial credit.
Actually, let me cut you off there, because one of the things that, the faculty, we've been meeting amongst ourselves through Zoom, of course, to try to figure these things out. And the overwhelming opinion is that we need to have different types of questions on our exams, forgetting how we're administering it, because of the circumstances, like for instance, to help avoid cheating and that kind of thing. We should be writing more questions that amount to short essays, so that you would be explaining something to me. What is the meaning of this integral, or what steps would you go through for this integral, or something like that. So it ends up being less calculation and then more description. I'm not really sure how well I can grade those things effectively, but at least it does get around the issue of somebody who does understand the general principles, but they make an arithmetic mistake.
So how would that translate on like a quest test, I guess?
That could not be quest. Well, I mean, I could write multiple choice questions to some extent and say, what is the meaning of this integral? And then I would give 3 or 4 different interpretations. And then it would be a question of not what's right and wrong, but what is the best interpretation of this integral, or something. It's hard. And I have to say, again, pedagogically, there's one little default in here. It's what's nice about those kinds of questions is they get away from just slavish calculations where, as you guys know, it's easy to make a minus sign error and you screw everything up. On the other hand, there are a lot of students who kind of have a nice fuzzy sense of what it is that we're doing, but they can't actually put that into practice. It's not, for them, it's not just a question of they add a couple of numbers wrong, but they don't quite know how to write down a function in the first place that's going to play the role of the capital T that I just described. So they're sort of listening in and nodding, and it feels comfortable, but they don't have enough grasp of the details to dive in. So, I mean, I guess what I'm telling you guys is that no matter what we do, I'm going to be a little dissatisfied, and I'm sure you're going to feel dissatisfied too. But I'll go with whatever you guys think is best. I guess what I'm hearing from you guys is that there's nothing wrong with some quest-like questions, but you still want to have some pre-response questions like the ones I had on the first exam. Would that be?
Yes. I think like the format of your test, like your first midterm, was fine. And I think like scanning wouldn't be too big of an issue on Canvas if you just add extra time for us to be able to like upload it. But yeah, I think overall like that format was great. It's just a matter of like, I want to be given credit when like you would have given me credit if it hadn't been like for this entire debacle. So
yeah, right.
Yeah. And my whole deal was literally one sentence: can we have partial credit, please?
Yes, for a free response, and obviously no for a multiple choice. I don't know. Although I got to tell you, my stepson had an occasion with a multiple choice exam that he had to do online because he's in college and they have to do everything online now. And his instructor screwed up, and he had a multiple choice exam where for every one of the questions, the right answer, or some of the answers anyway, were written twice. And the machine was coded to say that it's answer B that's correct. And he answered D, which actually was an identical answer. It just happened to not be the same as B, and so the computer marked it wrong, and so he wanted at least partial credit for getting another answer that was right. Anyway, yes, I think you guys should have some partial credit if I can arrange it. I mean, on the flip side, anybody who gets a grade at the end of the semester that they don't care for can just switch to a pass. So on some level, grades are maybe less significant this semester. I'm not really sure.
Okay, thank you for addressing that.
Yes, I'm happy to do it. And I know now we are out of time. I guess we're sort of migrating to that we're going to do basically the same kind of an exam as we had the first midterm, except that you'll have to scan things in, and I'll have to give you extra time, obviously, for a variety of reasons. So anyway, if you have any more comments, please send them to me by email, and I'll have a look at that. Otherwise, that's what we'll go with. The exam will be 2 weeks from today. That'll be the 24th, I guess. So keep working on that. Keep working on these homework problems. Something else I wanted you to do. Oh, yeah. Can you also address the question of, is this the right format for us to have for our classes? So as you noticed, I had some pre-prepared slides for today. I could do them all and just record the video and put it on YouTube, like I am putting them on YouTube. It just wouldn't be live, and then, I don't know, maybe you would feel a little more free to look at the videos online, you know, at a time that's better for you.
The opportunity to ask questions or during the lecture, it just helps with understanding.
So that's a vote in favor of keeping what we're doing? Okay.
Yes.
Okay. All right. Well, for that too, if you feel strongly, just send me a note, and I'll keep that in mind. I'm happy to keep doing what we're doing, but if something else works better for you guys, now's a good time. It's been 2 weeks, and it's a good time to address that.
I like the YouTube, Ellie.
You just want them all on YouTube? I mean,
it's helpful.
The only thing that would be sort of advantageous to making them all prepared in advance and then putting them on YouTube is that if I'm preparing them in advance, I can edit the videos, edit my slides a little more carefully, so they would be a little more professional. But then, yeah, then you lose the interaction, which is something that I also wanted.
I think like a happy medium between the two is that you do have like this class from 11 to 1 technically, because you have 2 sections. So like you could have the video in advance for one and then just provide both classes with your like 12 to 1 class. And then if we have questions, we can just like hop in and ask you questions.
Yes, there could be students who have another 12 to 1 o'clock class that they have to be at, and then they would not be able to switch, you know. So
yeah, so that's actually one of my concerns is I have other things throughout the day that sadly does not enable me to sit in from 12 to 1.
Right. Right. I definitely do not want to be in a position where you guys are forced to be with me at a time other than the original time. In fact, I've been putting the other things on YouTube just so that, I mean, some of you might have, you know, family responsibilities or jobs or something now. And if you can't come to these regular classes, then at least you can go on YouTube and download it later. So we're trying to make sure that everybody has an asynchronous option. All right, well, for the default will be that we'll just continue what we've been doing, but you know, anything that you guys can suggest that'll make this a better learning experience for you. I know everything just kind of sucks a little bit, so if we can improve it in any way, I'm open to suggestions.
You do also have like office hours from at 1 and 3 though. On
That's
Monday.
correct. That's correct. And some of you have already noticed if you can't make those office hours, I've been able to add some additional ones just on a one-to-one basis. So, because just like you guys, I'm not going anywhere. I'm stuck here at home. So, all right, but I'm going to have to cut this short now because I do have my other class coming in. If you want to listen in, you're welcome to follow their link and join in. Hey, and by the way, there's another teacher of Math 427L. She is doing the pre-recorded lectures. I think hers are maybe better quality. So I'm not sure where they are online. If you want them, I can try to find them and see if you guys can have access to those too.
Thank you so much.
All righty, have a good weekend, you guys, and I'll see you on Monday.